Okay, so we're very happy to have Laurie Kirby here to talk, to give again another encore of a talk from Cornell called The Winding Road to Mathematical Independence Results for PA. Go ahead.
Thank you. I'm looking briefly, it looks like several of you were there at that talk. So I will be reprising some of it, but I'll also be talking about getting into more than I did then. And I'm going to begin with a well-known quote from John Barwise, who was editor of the Handbook of Mathematical Logic. This is his editor's note to the Harris-Harrington paper, 1977. Excuse me. As Ken McAloon told us last week, Barwise was eager to include this paper at the last minute. So Harrington wrote it up in a hurry. And being Harrington, in the process, he more or less invented a whole new proof. And Barwise himself typed it. But anyway, I've put in boldface, as you see, the four criteria that Barwise mentions for why he likes this result. Since 1931, that is since incompleteness theorems, mathematicians have been looking for a strictly mathematical example of an incompleteness in first order PA, one which is mathematically simple and interesting, which I would read as mathematically interesting, and does not require the numerical coding of notions from logic. The first examples were found in 1977. So this, in a way, tells what you might call the accepted story. At the bottom of the slide, there's a couple of criteria I would add that made me excited at the time. It was first that it does not work by self-reference or diagonalization. And second, that has a model theoretic proof. Now, actually, the proof in the handbook is, Harrington's proof is not model theoretic. It proceeds by showing that the statement implies con PA more conventionally, and then calls on incompleteness. But as you know, Paris's proof was, well, all these criteria are a little fuzzy around the edge, but his proof, which you can find in the JSL in 78, is more model theoretic. So more recently, a few authors, and I'm going to mention briefly Smerinsky, von Plato, Ratjian, and Kripke, dispute this narrative and claim that either A, there was no such search, or B, anyway, others found such statements earlier, and usually Gentzen and Goodstein are mentioned, or both A and B. Kripke, who's the most polemical of these authors, certainly holds both A and B, even though you might argue that they contradict each other somewhat. But here's an example of a quote from Smerinsky in 2010. The first natural non-Gödelian arithmetic statement unprovable in PA was induction up to epsilon 0, shown underivable by Gentzen. So, of course, when I saw these, my first reaction was the natural instinct to defend my turf, since I have a small part in this story. But beyond that, it made me want to go back and understand better what it was that the people in the earlier generation, Gentzen and Goodstein, were actually doing and what their aims were.
A question?
Yes.
What Smerinsky is pointing out is not a statement, but a method, or if you like, a rule. I mean, there's no particular statement that he's pointing to, is he?
Well, he
Correct me
uses
if I'm
the word.
wrong.
He uses the word arithmetical statement. So, yes, we're often going to find here that things are a little fuzzy around the edges.
Yeah.
Yeah, and words like natural, of course, as the next slide will show, because here's a contrasting quote from Simpson in '83, talking about a remarkable breakthrough with the problem of finding natural sentences in the language of PA that are neither provable nor refutable in PA. Examples of such sentences were discovered long ago by Gödel and Gentzen, but unfortunately, those examples are not natural from a strictly mathematical point of view. These sentences appeal to logicians, but not to mathematicians. So natural to some and not to others. But anyway, this does suggest that there was the search that Barwise is describing. And I'm going to quote, last week, Roman gave us an interesting quote from Mostowski. This is another one which is rather long, 2 slides worth, but I think it's illuminating. This is in 1955 in a survey monograph on foundations of mathematics. Mostowski says that from Gödel's and Tarski's work, the problem arises whether it is possible to extend the notion of an axiomatic system so as to permit the wording of an arbitrary inductive definition. Such a system could be accepted as the arithmetic of natural numbers. The ultimate re-establishment of the foundations of arithmetic belongs therefore to philosophy and not to mathematics. So that's the ultimate foundations of arithmetic. But he goes on like this. There exist many other secondary but nevertheless important and interesting problems connected with the axioms of the arithmetic of natural numbers. And he singles out 3. First, the investigating the structure of the non-standard models. Second, to find out whether by using non-standard models it would be possible to obtain proofs for the independence of classical number theoretical problems of the system of arithmetic. And third, to prove the incompleteness of the axiomatic arithmetic without using the method of arithmetization by giving suitable models. Okay, so then again, there is evidence that there was such a search or problem. Interestingly, if you look at Mostowski's 3 problems today, with the first and the third, we've got a long way, I think, but the second, we've got almost nowhere, unless we're accepting weak systems of arithmetic. So what I'm mostly going to do is try and look back at Gentzen and Goodstein and see what they were doing and what they thought they were doing. But first, a couple other shorter topics. But first, maybe I'll ask if there are questions or comments on whether you think there was this search that Barwise describes. Okay. So yeah, first I want to just mention one just small thing, but to me it's an interesting cautionary tale about historical hindsight, because in 1976 or so we had this diagram here. And in 2004, when I saw Slayman's beautiful theorem down below, I said, oh, of course, at least as a conjecture, it's yes, of course. So actually, the proof is non-trivial, and it does require X, but to me, that was a lesson that you can look back into the past and think people knew something, or that they should have known something, and that's much easier to say with hindsight. But so before going to the even more ancient history, I'll just mention the run up to the Paris-Harrington, which I think really started with Paris's insight about that initial segments, models of PA, can be looked at as analogues of limit ordinals in set theory. And he noticed that if you try to look at inaccessible ordinals in this way, which means regular limits, then it splits in our context into two, regular and semi-regular. And kind of out of this work, the importance of, well, B sigma 2 in particular and B sigma n started to come out. It was around about this stage that he recruited me as his graduate student. So I played a junior role in this part when we were, you could say, looking at the first of Mostowski's 3 problems, which is the structure of models. So after inaccessible, we come, the next thing in the ladder of large cardinals is weakly compact. So that's what led us to Ramsey's theorem. Path to Ramsey's theorem took a detour really via transfinite set theory, and the path to the independence results was via, as I said, studying the structure of embeddings of a model. So it didn't come about through Barwise's search, that's for sure. In through the back door. That project of taking initial segments as analogues of limit ordinals didn't really get much further. So there might be more there. If you look, say, at a measurable cardinal, you can kind of talk about that in third order arithmetic, maybe, but then it gets too hard for me. Okay, so going back to the earlier generation, there's some interesting points about Ramsey's theorem from 1928. As you know, I'm sure he devised this theorem and proved it in order to prove a meta-mathematical result, namely solving the decision problem for a subclass of first-order logic. So maybe it's not surprising that it has mathematical import built in. And we can make a few comments about this. This is one of the many areas today I'm going to talk about in which I'm not an expert, but it seems that the boundary of decidability here is a little complicated, but basically Ramsey gave the best or close to the best. You can't add more quantifiers. Second comment is that ironically, and I know this from a paper by Hugh Mellor, and he doesn't give chapter and verse, so I Not sure how this works, but he says it can be done, the mathematical result can be done without using Ramsey's theorem anyway. And the other thing that strikes me about this paper is it seems to be the first use of indiscernibles. And again, someone might correct me on that, but it's certainly an early use of indiscernibles, coming right in with Ramsey's theorem. And of course, they're used in the set theory and in some proofs of Harris-Harrington and so forth. Okay, and then a couple of remarks about the later history of Ramsey's theorem. We have Specker's theorem of 1971 that the recursive Ramsey theorem fails, meaning there's a recursive partition without a recursive homogeneous set. And Yokush takes that much further and explores the recursion theoretic strength. And basically, to get the homogeneous set, you have to do a Turing jump. So maybe that was or should have been some kind of hint that there could have been some independence lurking in there. I don't know. And I wasn't aware of that, Yokush, but I dare say Jeff was. And I also wasn't aware of the Ramsey theorem, Ramsey theory, just at that period in the 70s was emerging as a field. Okay. Okay, so Gentzen's theorem, and again, some of you know far more about this than I do, but we can define epsilon zero induction to be the second order statement for all descending sequences of ordinals below epsilon zero are finite. And Gentzen proved in effect that on a base of primitive or recursive arithmetic, epsilon zero induction proofs con PA. Okay, his interest is not to obtain independence results for PA as we would understand them. His interest is in proving the consistency of PA. This is still close to the shock of the incompleteness theorems. People were still worried about proving finitistically the consistency of arithmetic. As you saw 20 years later by Mostowski's time, Mostowski kind of shunts that problem off to philosophy, and the mathematical concerns of are more modern in feeling, the same sort of problems we would address. But anyway, so Gentzen's aim was to verify the consistency of elementary number theory by means of techniques which in part no longer belong to elementary number theory. And elementary number theory in those days, we can read as first order PA. But which can nevertheless be considered to be more reliable than the doubtful components of elementary number theory itself. Now, we can express this a little differently, and this is what is often actually called, justifiably, Gentzen's theorem. We can express the notion that all primitive recursive descending sequences of ordinals below epsilon zero are finite as a first order statement. And of course, it's exactly what you need to push through Gentzen's proof, since it proves primitive recursive things. So now we've reduced it to a first order statement, which is not provable in PA. This is certainly implicit in Gentzen's work. I've read a couple of Gentzen's 4 proofs of his theorem, and you can certainly see that it's primitive recursive arithmetic that's kind of his base theory. I did do a full text search of Gentzen's collected works, and he nowhere mentions primitive recursive or primitive recursion. So again, these things are fuzzy around the edges. There's different ways you can interpret the language of the 1930s, but so certainly this theorem is at least implicit in Gentzen's work. If you compare it to Barwise's criteria, well, it fails big time, the one about not coding, not having arithmetical coding of logical notions, and the simplicity could be questioned and so on. So it's kind of there. And there's another caveat, which has to do with this asterisk on my slide here, because it's easy for us to express that statement I put in quotes there as a first order statement. I'm not sure how easy that would have been in the 30s. Again, some of you might understand this more than me, but it seemed that at least before Henkin's arithmetization methods in the 40s, which not so much the arithmetized completeness theorem itself, but its methods, that might not have been obvious that we can express that there's all sorts of other intervening work which kind of help us to take for granted that kind of primitive recursive Gentzen theorems being first order, like Preisel's and Loeb and Wehner, and the hierarchies there. By the way, Loeb was Goodstein's student, and Wehner was Loeb's student. And again, the codification of primitive recursiveness in the 50s, Pater wrote a book on it in 51, I think. Okay, before moving on to Gentzen, before moving away from Gentzen's theorem, a couple of notes. Kripke in the paper, which I've put approximately 2021 because it was published online last year in the journal History and Philosophy of Logic. Last time I checked, it didn't have an issue number assigned, but he makes a claim that TI subscript epsilon 0 was a mathematical independence result of Gentzen, where that's the first order schema. We're asserting for every formula phi that phi does not define an infinite descending sequence below epsilon 0. To me, it seems bending the rules a little bit too far to see a schema as a independence result. The schema is an essentially first order thing, so it might not seem natural to a non-logician. The other thing I wanted mention about Gentzen's theorem is just this baby example of something that I always struggled to understand about Gentzen's theorem, which is the explosive growth rate of the proof size that you get with the cut elimination. So what I'm going to do here is grossly oversimplified, and as I said, I'm not an expert at all, but this really helped me with an intuition which will come in useful later on. So what we're doing in these, there's two proof trees here. The proof tree on the left there, let's look at that. At the bottom is B and C. So what we have here is a proof of B and C by modus ponens. So modus ponens is actually a special case of cut, and it helps to simplify the example. And as Ken said last week, this way of looking at proofs always feels unnatural to maybe to those of us who come from a model theoretic background, even though it's called natural deduction. But anyway, we're proving B and C by modus ponens, and the thing that modus ponens shares with cut is that it loses information, right? That we've lost to when we've inferred B and C, we've lost information that A of A. So there's proof on the left. Then the green part of the proof is basically the definition of conjunction. So in the blue modus ponens in the bottom left, we somehow have a proof of A, which I've indicated schematically, and a proof of A arrows B and C, which I've indicated schematically, and each of those components has one. And the point of cut elimination is we want to get rid of that modus ponens. So as I said, there's a baby example doing modus ponens elimination, and we do it via the tree on the right. And you see what's happened. We're still deducing the same end result B and C, but we're doing it by first appealing in green at the bottom to the rules for conjunction, and then doing two modus ponens. So actually we haven't eliminated modus ponens yet. We've got two. Crucial thing is, first, they're both simpler. Notice they're modus ponens applied to two simpler formulas, and also they're higher up the tree. So that's what we're going to do. We're going to iterate. But the problem is that if you look at the proof on the right, we've potentially doubled its size, because that sort of orange fire above A there, there's now two of them in our new proof, and that could have been the bulk of the proof. So we've doubled in size, and we've done that merely to move the modus ponens problem one level up. But so we have to iterate basically as many levels as the tree has, and that's where the doubling comes from. You might have to iterate by an exponential amount in, say, the height or complexity of the tree. But that was only eliminating a single modus ponens. So we now have to keep iterating the whole process again, and then maybe modus ponens is at every level. So finally we get the iterated exponential growth in the proof size, which is the characteristic growth of primitive recursive functions. So as I said, we'll come back to that slightly, but this sort of picture was helpful for me. We're just looking at an induction step in the complexity of that formula we started off with at the bottom left, B and C.
It seems to me that we can avoid doubling the thing by dropping the demand that the thing is a tree, right?
Yes, so another way of putting that is this is an unnatural thing because it doesn't allow the concept of a lemma, right? Naturally, we would say lemma A and prove A, and then we would be allowed to refer back to that lemma. But here it's as if we have to prove it anew each time. But that's part of what's needed to eliminate the cut. That's how I read it. Anyway, Goodstein's theorem, and this is, I'm assuming this definition is familiar to you. Goodstein sequence starting at n. At each stage n, you have a number in pure base n form, and you replace all the occurrences of n by n plus 1 and subtract 1. And you have what's normally called Goodstein's theorem, but for the purposes of this talk, I shall call the special Goodstein theorem, or SGT, which says for every m, the Goodstein sequence starting at n terminates at 0. And this is a theorem that myself and Paris showed is not provable in PA. In this work, unlike the earlier work, we were equal partners, I'd say. So it was Jeff who found this obscure wartime article by Goodstein, which had the, which I'll be discussing next. But Goodstein nowhere mentions this theorem in this form. He actually proves, as some of you know, something much stronger. So let's, for any function f from omega to omega, we can define the f Goodstein sequence, which basically means f is enumerating the bases. So at stage n, we're in base fn form, and we replace all occurrences of f of n by f of n plus 1. Fact 1. So the general Goodstein theorem, as I'm going to denote it here, is what Goodstein actually shows in his paper, that for every non-decreasing f and for every n, the f Goodstein sequence terminates at 0, which, as stated, of course, is a second order statement. So why was he doing this? His basic trick was that he saw that in the Cantor normal form, you can simulate the base omega by a sufficiently large base n, bigger than any of the coefficients around, and you can preserve the ordering. And this led him to what I'm calling GGT, his theorem, and also the fact that the reason he isolates the theorem is that it's equivalent to epsilon 0 induction. So he's perfectly aware that this is not a first order statement. His aim is he's concerned with what he calls finite constructive proofs of consistency. So in this sense, he's closer to the 30s than the 50s. He's still worrying about proving consistency of arithmetic. He's close to Wittgenstein, in as much as anyone could be said to have been close to Wittgenstein. He was one of Wittgenstein's favored students in the 30s. And he follows Wittgenstein in being a strict finitist and eschewing and distrusting quantifiers over the infinite.
A question?
Yes.
Was Wittgenstein actually finitist? I'm not quite sure of that.
No, my answer is not no, excuse me. You're right not to be sure of it. I'm the last person to be sure of anything about Wittgenstein. I would say this, that Wittgenstein proceeded by asking questions, and maybe that's why it's hard to answer your question. Goodstein was probably more Catholic than the Pope and could be dogmatic. And as I say here, he indulges in what Barwise complains about as polemics against the usual mathematical logics. Not in this paper, but in earlier papers.
Thanks.
Anybody else? Okay, I better move on. So let's see. Goodstein's aims were not about, therefore, independence results from first-order arithmetic. He wasn't even interested in first-order arithmetic. So for us, it's a pi-1-1 statement. How could he finitistically talk about this? Well, he uses, basically uses f as a free function variable. So he thinks of his statement as written with a free f, which you can, I guess, justify finitistically. It just says, give me f, and I can plug it in, I suppose. Later on, he'll write a couple of books about this. As I mentioned, he doesn't mention the special case SGT. He does stress the number theoretic nature of his result. That is, that he has found a number theoretic nature, a number theoretic equivalent to epsilon zero induction. And this last point on the slide here is what he considers most important, because in a letter to Bernays trailing this paper, this is the result he singles out. He's giving his trick to get what he calls a completely finitist proof of induction up to a tower of 3 omegas. In fact, this takes up a good half of his paper. And he says the method of proof readily extends to ordinals beyond 3 omegas, but to reach 4 omegas by these means seems hardly to be worth the labor involved. Now here's where we come to von Plato, because von Plato, in a Mathematical Intelligencer article in 2014, discovered in the Bernays archives his correspondence with Goodstein about his paper, and papers, plural. Bernays was a referee. Apparently, the anonymity of referees was not yet in place. I don't know when that came into place, or maybe they relaxed the standards in wartime, I don't know, because letters were taking weeks and months. But anyway, Goodstein submitted his paper to the JSL, which meant church, in Princeton, and then Princeton sent it off to Bernays. Bernays corresponded with Goodstein. So it seems in one of these papers that Bernays dissuaded him from making a claim about independence of his result, GGT, in part because his claim was based on a conjecture which Goodstein did not prove. Conjecture does survive in the published paper. We don't seem to have the his paper, Goodstein conjecture. It definitely hedged around with "it is likely that" thing. Induction up to any given finite tower of omegas must be capable of a finite constructive proof, which again to him is not the same as a first order proof, but epsilon zero induction is not so capable. So he did make that induction, not about his own theorem, but about Gentzen's theorem as a conjecture. But what exactly was the claim that Bernays dissuaded him from? As I said, we don't have the original submission. What we have is Bernays's draft of his letter to Goodstein. So Bernays kept his rough draft, I guess, in his own files, where he says, perhaps on account of these circumstances, it would be best to cancel the paragraph on the undecidability of P in Z star. And here, P is Goodstein's name for Goodstein's theorem. But what's Z star mean? It's unlikely to mean anything we could regard it as first order arithmetic. Von Plato does take it to be Gentzen, well, against the Gentzen system, which we can identify with Hilbert's Cylon theory and with first order PA and with what they called elementary number theory. But of course, GGT makes no sense in that language. And also, Bernays' next sentence suggests that Z star is something else, because his next sentence says, parenthetically, this would also have the advantage that you need not at all introduce the system Z star. So Z star was something that was introduced by Goodstein. And if we look at, here's where we get to the historical sleuthing, because if we look at Bernays' letter more closely, there's only one reasonable thing that Z star could have been, which is basically expressing arithmetic in terms of Goodstein's equation calculus, so allowing free function symbols but no quantifiers. Because in that system you can express GGT, so you can express that what we would call a pi1 statement by leaving the function free. Time is pressing on, so I won't go into too much detail about that second paragraph here. But Bernays points out that although GGT can be expressed in Z star, its negation cannot. So that's what leads me to think that Z star is the Goodstein equation calculus. By the way, another thing Goodstein tends to say about his equation calculus is that it's got rid of the arithmetic, there's only logic. Okay, so at the bottom there, I just noted that was a standard Z star at that period, which is Hilbert's system, which is essentially PA plus the omega rule, but this also can't express general Goodstein theorem, so I don't think Goodstein was talking about that. But the summary of all that is that Goodstein did claim an independence result. It wasn't proved and it was withdrawn. We have Goodstein's letter confirming he withdrew it. But it wasn't about first order logic. But nonetheless, it was an independence result for his theorems. And I'm sure it's true. Von Plato in his article uses the same name for, I'm calling SGT and GGT, calls them both Goodstein's theorem, and that could lead the casual reader to think that Goodstein knew the independence of SGT. We can rescue Goodstein in this sense, just like we did for Gentzen. So Goodstein could have done this. We can state a primitive recursive Goodstein theorem, or PRGT, which just says you just talk about the primitive recursive f. Of course, that's all you need to get the primitive version of epsilon zero induction. And this is or can be written as a first order statement and is a bona fide independence result. But this suffers from the same defects as what I said for the primitive recursive Gentzen theorem. First of all, I don't think this could have been done in the 30s, so I may be wrong. And second, it certainly codes logical notions and is not very simple. Now, this theorem goes back to the baby example of Gentzen's theorem I gave, because it's here where you see you need that primitive recursive growth that you saw in my picture translates to primitive recursive growth of the coefficients in Cantor normal form, and that translates to primitive recursive notion of the primitive recursive growth of the coefficients in the Goodstein sequence, which means you need the bases to grow fast to catch up. So the primitive recursive Goodstein theorem is rather natural equivalent to the primitive recursive epsilon zero induction. What Paris and I prove is a stronger result than one I think Goodstein even could or might have claimed, because we proved the independence of SGT, which is a special case and is weaker than PRGT. Statement, the independence of SGT is a stronger result. So it turns out, as a corollary of our results, the two are actually equivalent. Basically, once you have the machinery like all those concrete independence results, you actually get everything, you get one consistency, so they're all equivalent. In a paper by Ratchen in 2015, that he gives a proof of independence of the Goodstein by special Goodstein by kind of separating out the stage. The translation of Gentzen's theorem to PRGT is simple, and then he separates out the proof that SGT implies PRGT, which you can do. He does combinatorially, you can kind of pad out those descending sequences. Okay. So, summary, Goodstein's method doesn't give the independence results for SGT. You have to work harder. And yes, someone in the late 50s could have had the tools to prove PRGT or maybe even SGT, who knows, but they didn't. And we can say the same thing about the hydra. The hydra doesn't even need Goodstein's trick, so it's kind of would have been easier to find in a way. Someone in the late 50s, say, could have proved the independence of the hydra statement, but again, most likely in a form where you would need the number of new heads, which kind of correspond to the coefficients. That has to grow primitively, recursively, not just one more each time. By the way, the hydra statement, as we had it, and it does not satisfy those Barwise criteria, because if you say Hercules can't lose, you have to quantify over primitive recursive strategies or something like that. So it seems to me you've introduced logic, and it has other virtues maybe, but you couldn't maybe claim it as a as satisfying the Barwise criteria. You can rescue that. Oh, by the way, yes, the in Kripke paper I mentioned, there's a couple of errors that shouldn't have got through peer review, but for instance, he states that the hydra statement is pi03 when in fact pi02. But yes, you need the number of new heads to grow primitive recursively, because proofs grow like that. But you can rescue that by taking the worst possible strategy for Hercules. So if you try playing the game and you think, what's the stupidest thing that Hercules could do, that defines a particular strategy, and then you can show that that strategy is independent. But you certainly lose some simplicity. And my last slide is just to mention a couple other candidates, which are serious candidates that I haven't had time to address. Early mathematical independence results. First, certainly from the universal Diophantine equations, from the MRDP theorem, you can get a Diophantine independent statement. Arguably, I think you're coding logical notions, and they're certainly not simple, and they certainly weren't in the 70s. Second point is I think there's a more interesting discussion to be had here. Prizes results, which characterize the growth rate of the provable recursive functions in PA. Which of course is epsilon 0. It's a hierarchy of length epsilon 0. So kind of diagonalizing out of that gives you a function whose which is unprovable, whose function whose totality is unprovable. So that could be another discussion, but I'm going to stop there and hope there are some questions. Thank you.
Okay, thank you, Laurie. Let's thank our speaker. And let's open up for questions. So feel free to just jump in if you have one, or raise your and unmute yourself.
Well, to get things started, a quick remark. You mentioned looking for more connections between large cardinals and independence statements. That's the Cautionary-Maclaurin theorem. I admit that's a bit self-referential, but still, is sort of inspired by regressive functions on measurable cardinals.
Yes. That's right. I was thinking more in terms of pursuing it higher up the hierarchy, and I know you, of course, got probably further than anyone, right, with Freeman and Simpson in that way. But yes, there are equivalents from the result you mentioned was at the same level, as it were, weakly compact, right? But your other result went higher because it went to that. I don't know what kind of large cardinal that would have represented.
Yeah, that was inspired by a theorem, a Ramsey kind of theorem for a structure called the barrier.
Right.
And unfortunately, I can't find any reference. When I look up barrier, in mathematics on the internet, all I can find is something in harmonic analysis. So I've lost track of the barrier.
Are you talking about the Nash-Williams theorem?
Yes, yes,
Okay.
yes. Maybe that'll get it for me. Thanks.
Other questions?
I have a corny joke
Go ahead.
that I was going to insert into my talk last week, but somehow I didn't dare put it in the slides, but somehow I missed it. But it involves Laurence Kirby and Peter Clote. And when Laurie was in that period in Paris, when we had all this going on, Laurie was there, and he and Peter Clote would play music in the subways. They were buskers. They'd play in the metro. And the piece that they were famous for was their piano concerto, the Giuseppe piano concerto.
Well done.
I'll leave the rest of you to decide what small kernel of truth there may be inside.
Now, but Laurie played violin and Peter plays flute.
That's great. Okay, so I'll stop the recording here. We can continue the discussion if there is any. And next week we have one more talk. It's at a later time, so just be aware of that. Okay.